All right, so welcome back and hello to everybody on Zoom. Hello. I know there are some people who just joined the course today for the first time, so I need to do some summary of the housekeeping. This is the website which is going to service the course. So I'll use Quarkus, and you know that I'm using that for things that I cannot avoid using Quarkus. But for everything else, I use this. Quarkus doesn't give me enough resources, and it's very complicated to use. Some of you already noticed that I think I made a mistake on assignment number 1. I made 2 mistakes. I'm not sure how many of them you realize. You have to go and fix them. Eventually it works, but it's very, so I feel more comfortable on my own website. And everything about the course is here. You have the Zoom link, you have some marketing information about the course, this and that. And the key, the textbook. There is, if you need a textbook, I wrote a textbook on Top Hat that you can access, you can buy, and I don't know how much it costs, but it's there if you need a textbook, okay? I recommend it. It is good alternative reading, but everything that I do in the course is on lecture notes that you can find on the reading room. So the reading room part of the course is what contains all of the lecture notes I will be using here. The one of last week is there. That lecture note is there from last time. The one from today is also there. It's updated, and the ones that I will be lecturing on the next days, they are there, although those are probably going to be changed, okay? I'll probably change them, I'll update them. And for sure I'm going to include a new one this year on climate risk, but that I don't have it yet. I mean, I have it, but not for this course. I taught a course earlier this year on climate risk. I have to adapt it for this course. So the lecture notes are there, and there you also have a link to a few things. You have a link to, I have a number of YouTube playlists. I started doing this the year of COVID, so that year I have it on YouTube, the entire course. Last year also, and this year there's a new playlist, and that contains the first lecture that we did here last week. That's there too. Okay, so you can see those lectures there. So the videos are there. The lecture notes are there. The assignment 1 is there. Assignment 2 will be there too. The website that you need for assignment number 1 is there also, as well as other things that I consider interesting. Okay, if at some point you want to watch YouTube, you have no idea what to watch, you can click these videos randomly and you'll see something which is useful and entertaining. If at some point you want to read something and you're not sure what to read, you can read some of these notes. I don't have a lot for this course because I have a lot of lecture notes of my own. But if you go to some of my other courses, there's a lot. You can spend the entire year reading interesting things. I have a lot of interesting papers there, okay? That's my own little library. If any one of you has a particular interest in any particular topic, you let me know and I'll put things there. I like to build these kinds of things, okay? And then I also have some books. This, when possible, I've tried to include the link to the electronic version of the book at Roberts. So if you click on the link, the book should come right up on your screen and you can read it there, when possible, okay? So this is the way I like to organize the course. So everything is there. What is not there are the quizzes. The quizzes are on Quarkus. You should have received the first quiz already. And for those of you who were not here last week and you don't understand what that quiz is about, you have to watch the video that I showed last week, and then you can do the quiz. Don't do the quiz before watching the video. It'll make no sense to you, okay? I think I'm done. Any questions? Anything that I missed from the summary of what this course is about? Anybody? Any questions? Did I miss anything? No? All good? Yeah? You have to speak louder.
Can we download?
Yes, you can. When you open them, when you click there, they say download function. Okay?
No?
No? Let me show you. So let me click. So this is last week's, right there. There's a download button right there. All right? Sometimes, Top Hat, I have to assign the chapter, each chapter at a time. Sometimes I forget, okay? So I may be late. I'll try to remember to assign today's chapter today so you can read it. And there's some homework questions for you to do and this and that. So I'll try to do that. All right. So what I'm doing today is I'm going to, today I'll be a mathematician, and you too. Whereas last week I focused on the business aspects of this course. Today I will focus on the mathematical aspects of this course. This is something I mentioned last week, and today we're going to make a very big deal out of this. Okay, this is going to be actually what we will develop today. I mentioned something last week, which is the difference between things that exist in the financial markets and things that we invent, things that we make up. Okay, and I mentioned the example. You take an apple that falls from the tree, the apple is real, the tree is real, and the apple falling is real. But then the law of gravity is not real, you make it up. It helps you explain where the apple falls from the tree. We're going to do the same thing here. It's a mistake to think that interest rates are real, for example. They're not. When someone buys or sells a bond, you buy the bond and you pay. That's what's real. The bond is real, the payment for the bond is real, the money you use is real, and the coupon payments you get are real. Yeah, the interest rate is not real. It's what helps you understand if that was a good deal or not. Right? That's why we want to know interest rate. It gives us a frame of reference, and that's where math becomes very interesting because it helps us understand what's happening. And last week we saw two definitions of what's called yield. Yield is the sophisticated term for the interest rate. Okay? There's a few things that we saw that I'm not going to repeat. We saw the difference between compounding, say annual, quarterly. We saw instantaneous compounding where the power is replaced by the exponential and all of that. We saw that last week. Okay, I don't know if that was new to you or not, but that's elementary things. I'm not going to repeat that. And there were two possible definitions of yield. One, which is the one that people who don't know a lot of math use, is this one here. I call that yield to maturity. Everybody calls them yield. You have to be alert and then understand what do people call yield. So the key is this. If yield to maturity is the usual convention, is something that depends on the bond. So given a bond, each bond is going to have a yield to maturity, R. You will see that on the website from where you get the bond price information. In the newspaper clipping that I showed last week, you see it there also. It's a convention. When people talk about a bond, they mention the yield of that bond. Okay, so it's a function of the bond. You need to understand. It's a function, something that takes one space into another. So this takes bonds into real numbers. All right? Okay. And the way to define it is very, very simple. It's so simple that that's why people love it. Okay? It's here. This is the definition. Very, very simple. Given a bond, you calculate R. Now, something important to notice here is the distinction between the dirty price and the clean price. When you do a bond trade, the price that you pay is usually quoted to be what's called the clean price. It's not the actual price you pay. The analogy is like when you buy a sweater. It says $29.99, but when it's time to pay, you pay $29.98 plus HST. This is not a tax, this is not HST, it's nothing like that, but you think about it like that. You have to pay something else, which is the accrued interest on the coupon payments, right? The idea is that when you buy that bond, you're going to get a coupon payment which would be a little bit larger than it should be. Some of that money belongs to the seller. How much money belongs to the seller? Well, the formula is here. You just give it to them. All right? That's the idea, is to prorate the next coupon payment to see how much goes to the other. And this is not part of the quoted price. The reason is for tax purposes, one of the payments leads to capital gains, the other one is income. And as you know, if you have studied accounting, income and capital gains, you cannot mix. That's what's called dirty, right? So clean is clean. And then the accrued interest is clean too, okay? But they're different. You put them together, they're dirty. But for us as mathematicians, the real value that is paid is everything. So mathematicians like to work with dirty prices, okay? Which is both of them combined. And that's why the yield is calculated using the dirty price. If you calculate the yield using the clean price, you're doing something terrible, okay? Because you are doing a mathematical construct on the wrong market information. Tax is not relevant for the calculation of R. The calculation of R is basically a statement of the price of time. So you need to do the right accounting for that. You need to mix the two. You need the dirty price, okay? All right. So the thing is, if you look at the dirty price, there's no mystery here. This is very simple, okay? And calculus, whatever calculus you do, 135, 137, I don't know where you come from. That equation there is a monotone equation of R, so of course it's going to have a solution, right? And a unique solution. It's a monotone function. Easy, right? The problem is useless. Why? Because it depends on the bond. The biggest use that we will make of interest rates, it'll help us compare things. Because this already is a function of bonds, it's not going to be useful to compare anything. Moreover, we won't be able to use it for some of the applications that today we're going to be using. So we need to create a different mathematical construct that is going to be more robust for the applications we have in mind. That's where we go and create something different. And this is what we will call the yield. I call it the yield because I've been calling that the yield for a long time. Some people call it the spot rate. Some people call it a discount rate. There's lots of different names, maybe even more than I wrote here. Okay? It's not a big deal for me because I'm not going to use this. So when I talk about yield from now on, I'll be talking about the mathematical construct. And what is it? What it is as follows. Let's do what mathematicians do. Let's imagine. Let's imagine. Imagine I have a curve, which is a function of time. Not a function of the bond, a function of time. And by the way, if you're thinking, wait a minute, a bond has a maturity date, so a bond is time. No, it's not, because you can have two different bonds maturing on the same date, which are different if the coupon payment is different, right? And as you know, that's not an application. It's not a function. A function has to be a map, an application, right? So it won't work. It won't work, okay? So by doing this, I'm actually imposing something very important. I'm forcing my yield, which I haven't defined yet. I'm forcing my yield to be a function of time, only of time. But it has to price all bonds correctly. And again, by price, I mean the dirty price. We're already agreeing that the clean price is good for tax purposes only. For mathematical purposes, we need the dirty price, yes? Okay, so we need a curve that will price all of the bonds exactly. And the pricing is here. And if some of you were not here last week and you're confused why I'm using here the power and here the exponential, what's the answer? That on this side, I have annual compounding. On this side, I have instantaneous compounding. Okay, if you want annual compounding, it'll be here. But we don't like that. We like instantaneous compounding. The math becomes much easier. The mathematical models are much easier. And you can always go from annual to instantaneous and back. It's no problem, right? You could choose quarterly compounding. I'll have to say you're weird, because the mathematical model will be very complicated if you use quarterly. You can do it. It's no problem. But it'll be very complicated. And you gain nothing. So, you know, in math, we like simple models, right? So that's why we're not going to use annual compounding. From now on, we'll use instantaneous compounding. Every once in a while, we will come up with the annual compounding. Usually, if I'm going to show you for example, an exam question from the CFA or the FRM or something, I may do that because that's what people do. But I'm assuming you don't need that explanation. I'm assuming you can do the translation from quarterly, annual, instantaneous compounding. Yes? Okay. So we would like to have this. Today I'm going to prove, quote unquote, prove to you that this exists. Okay? I'm not going to prove it. I'm just going to convince you it exists. The proof will come later. Okay? We'll prove something different, something bigger than this. But today I'll convince you that this curve does exist. And we'll even get an idea how to calculate it. All right? But I want you to imagine what it is that we're aiming for. We're aiming for a curve that prices everything. Everything today. Tomorrow, the market will have changed, so the curve will have changed. So the dynamics of that curve, how it changes, that's a different issue. Our main issue right now is to build finance using that curve as our building block and forgetting about this. Clear? Does everybody understand the difference between the two? There's always people who don't, and it's okay. Please ask me now. Don't ask me next week. It's too late. Ask me now if it's not clear. Because it's very simple to explain. Is it clear to everybody? By the way, you can still ask me next week, okay? I prefer you ask me now. One is a function of time. The other one is a function of a bond. If you have 30 bonds listed, you have 30 values. The one we are creating is a mathematical construct, so in principle it should exist for every single real number bigger than 0. Of course, you already know we don't have enough bonds. We're going to have to make some simplifying assumptions, and we'll have to make some approximations. Sure, that's okay. We're already working with dirty prices, so we'll bring in some dirty math too. That's no problem. Yes? Yes? Okay. So if we're good with that, let me move on. So the other questions. Does this curve exist? If it does exist, how do we calculate it? There must be a way, because this is your assignment number 1, right? How does this curve change through time? And what else can we do with it? I'll answer all these questions today. The purpose of today's class is to answer all these questions, and a few more. All right? So the first thing that I'm going to do is I'm moving to the world of make-believe. Mathematicians, we like to do that. So you say, what if? And then we imagine something, and then something happens, and say, well, if that's the case, then I can do something different. So let's imagine a 0 coupon bond, a bond that pays no coupons. All right? Some people may tell you, oh, there are no bonds that pay no coupons. All bonds pay coupons. That's not true. First of all, if a bond matures in less than 6 months, it has no coupon payments, right? It had past coupon payments, but for the payments that remain, it has no coupons. So it's as if it has no coupons. That's what mathematicians do. For us, a bond that pays no coupons or a bond that has no coupons left to pay is the same thing. Okay? Also, or additionally, if you go to a bank and say, I want to buy a bond with no coupons, they'll make it for you. They'll charge you for it, but they'll make it for you. Dealers do that. So it is not a very big exaggeration to think of bonds that pay no coupons, 0 coupon bonds. And by the way, for the next 2 or 3 weeks, we're going to assume that everybody in the financial sector works for free. There are no fees. Only for a few weeks, okay? Only for a few weeks. In about a month or 2 months, we will start to see how fees come up, but later. Because it's easier to build a mathematical model assuming everybody works for free. All right. So when you look at the zero coupon bond, the zero coupon bond has a notional, which is the amount of money you're going to be paid at maturity. So if it's a $100 bond, but has a coupon payment that is no longer going to be paid, that still is part of the payment at the end. So if the coupon payment says $7 per year, then the notional for us would be 103.5. Because the notional in our definition is what you're going to be paid at the end. There's only one payment. Whatever that is, we call it notional. And we use the letter N to denote that. N, notional. Okay? Great. It has a price. Dirty price. And it has a time to maturity. If it's less than 6 months, sure, but we're imagining zero coupon bonds of all possible maturities. No restriction on that. We're mathematicians, we have a license to imagine things. So with that, with 3 variables, which are all here, P, N, and T, time to maturity, price, and notional, I define the yield to be that expression there. It's my definition for a zero coupon bond. Why am I defining? Well, I'm defining that because that's what I'm aiming for. If there are no coupon payments, you will see that these 2 expressions are the same. Right? But I'm not doing this because of that. No. This is my definition. Then this will be a consequence. All right? We act as mathematicians. We know what we want, so we just define things in that way so that the outcome is as expected. But it's very important. We don't want this, therefore we do that. No, this is my definition. This is my definition for zero coupon bonds. So this is good because I'm assuming there are zero coupon bonds of all possible maturities. Therefore, this curve is always defined. I don't know what the prices are, but the curve will be defined, right? Now, if this curve is defined, then what happens? If this curve is defined, then note one thing. If you have a bond that has coupon payments, the price has to be what's there. Has to be what's there. Why? The answer is not because of mathematical reasons. No, that would be wrong. Okay? Today we're going to introduce a new concept. It's the concept of arbitrage-free pricing. That's what I'm going to explain here. Okay, so the explanation of why a coupon-bearing bond will have this price is because of arbitrage-free pricing. First of all, mathematically it will be nice because that means that the pricing function will be a linear function. Nice, right? You can think of a coupon-bearing bond as a superposition of zero coupon bonds. One is a zero coupon bond that corresponds to the first coupon payment. The notional will be the first coupon payment, right? Another bond will be a zero coupon bond for the second coupon payment, and so on and so forth. So you're decomposing a coupon-bearing bond as a superposition of zero coupon bonds. That's what we're doing mathematically, right? And therefore, the price of those superposition bonds would be the sum, right? But in doing that, I'm assuming that prices are linear. And someone will say, why are prices linear? What if I buy 2 apples, that's the price of 1 apple plus another apple added together? Why is that? Well, there's a reason. There's actually a reason for that, and it's called arbitrage-free pricing. Imagine that the price of a zero coupon bond, the price of a coupon-bearing bond was not what that formula indicates. What would happen? Let's say cheaper. What would happen? What would happen is that in the financial markets, everybody would go and buy the cheap bond, and they would sell zero coupon bonds to people, right? And make a profit. And I told you, everybody works for free, right? So in economic language, what that means is that that leads to a price which is not in an equilibrium. So in this class, for a while, we're going to assume that all prices are in equilibrium, which means that no one should be able to make money for free. If something is too cheap, people are going to buy it and prices go up, right? So we're going to observe prices after they reach equilibrium. I'm not going to give now a speech about price formation. It's a very big deal in economics. Some of you may have seen that already, but I want you, everybody, to adopt the same perspective as I'm adopting, which is we only look at prices after they reach equilibrium. A footnote. The way people make money is by taking prices to equilibrium. You buy something cheap when people think it's expensive, right? Okay, who of you is buying Bitcoin right now? That would be an example, right? You buy Bitcoin, by that you drive the price up because you say, well, people are spooked, and then I think it's too cheap, so you buy Bitcoin. You drive the price up by doing that, and then you make money, right? So we're not doing that here. We're assuming prices are already at equilibrium. So the theory we're developing now is the theory of prices at equilibrium. That's why we can introduce the arbitrage-free condition, right? So that's why every bond is going to be priced like that. So this is nice because it means that this curve must exist, right? I'm not giving you a mathematical proof. The mathematical proof I'll give to you probably in 2 weeks. There's actually a mathematical proof, and I'll give it to you because it is going to prove lots of other things for us too. It's called the fundamental theorem of asset pricing. Today I'm just introducing this way of thinking applied to the yield curve. So if there is no arbitrage, then this curve must exist. Is that clear? You don't have a proof. There's no step 1 there for QED. There's not that. Okay? This is the way we think about that. So this curve must exist. Because zero coupon bonds must exist, and therefore they must be priced according to a yield curve that should price everything else. Because if not, then people will take advantage of the price difference. That's why. All right? It's not a mathematical proof. It's a financial proof. The mathematical proof will come later, 2 weeks. All right, so this is, you're all with me? Yeah? I'm assuming that if all of you guys are with me, the people on Zoom are with me too. What happened now? I wanted to, I don't know if I can hear the people on Zoom. I don't know. I don't know. Someone on Zoom wants to say something? See if I can hear you. Maybe people on Zoom are not speaking. That's fine. All right. So, So, if that's the case, then I'm going to immediately start to think about the curve dynamics. Because you will see why. Because I can calculate that yield curve exists every day, and then every day will be different. So I have a challenge now because I have to start to consider 2 time variables. One is the time of day, lowercase t, that's today, tomorrow, day after. And the other one, I call it capital T, is called tenor. That's a year from now, 2 years from now, a bond that matures in a year and a half. That capital T would be a year and a half. So now if we make that yield curve move through time, there's 2 time variables. We don't want to confuse them. Okay, understand? It's a curve that moves through time. It's a surface. So there's 2 time variables. And for zero coupon bonds, the price of zero coupon bonds is given by that. Assuming, I'm assuming notional of $1. Now I'm a real mathematician, right? Say, well, I like ones. Ones and zeros is your favorite numbers. Ones and zeros. So that's the price of my zero coupon bond over time, which means that the definition of the yield is going to be the logarithm of the price divided by the time to maturity. I haven't done anything. I'm just following my nose now. I did my definition earlier, 2 slides ago. All right? Good. So that means that we're done. That means that we're done. Some things, the price of my bond will always be between 0 and 1. Okay? Negative prices will imply negative interest rates. We don't like that in our mathematical models. Not that it doesn't happen, it has happened. But I'm not discussing that here today. Okay? Today we're developing mathematical models. In the mathematical models that we're going to develop, interest rates will not be negative. And also we assume no transaction costs, which means if you want to borrow $1 from me to give it back to me immediately, then it's $1. I don't charge you for that. All right. So these are some of the assumptions. Now, there is one thing called the instantaneous cost of borrowing, and that is the rate. So if I lend you $1 and you give it back to me a second later, okay, you'll pay something which is very, very close to $1, but not exactly $1. This, in practice, is a very important number. It used to be called Libor. And this is the rate at which banks lend each other for overnight lending. So let's say you're a bank and you close your operations at say 5 p.m. Right? Then you need to do you need to balance some of your balances, and you need to just, you owe some money to some bank, say, well, I'm not going to give you the money now, you have to give it back to me tomorrow, so you start lending money to each other overnight. That's what banks do, they lend money to each other overnight, okay? Every day. And they charge some money for that. This is what happens in practice. Mathematically, we deal with that by looking at my yield here and taking the limit when t goes to lowercase t. That would be the overnight lending rate. Yeah? And by the way, it's capital T going down to lowercase t, not lowercase t going up to uppercase t. What happens when you do that? What happens when you take that limit? Well, that's a derivative, right? Because you will say, well, that's plus log of 1, but 1 is the price of tt. That's 1. Right? So you can add a 0 there, which is that, and then you can see that when you take the limit, that becomes a derivative, a partial derivative, right? Everybody sees the derivative there when I take the limit?
Yeah, but why does that exist?
Why does the derivative exist? That's a very good question. Let me first make sure that everybody sees the derivative. Okay? Does everybody see the derivative there? If you don't see the derivative, please raise your hand or say something on Zoom. Everybody sees the derivative? I don't believe, someone does not see the derivative. I know there's someone here who doesn't see the derivative and is just too afraid. There you go. Oh, do you see the derivative? You don't? Okay, thank you, okay? And other people will be grateful to you too, okay? Okay, so let me see. I'm taking the limit when uppercase T goes to T, right? Okay, all right. So let's see, does it help if I add here log of P of TT? Does it help? What is that, by the way? That's 1, right? What's log of 1? So I can always put that there. Plus, minus, right? Or if you want, I could write log of p of lowercase t, comma t also, right? Or I could add log of 1. Doesn't matter. It's a 0, right? If I add it there, what happens here? I don't know what happens. Okay, so if I add this here, which is a 0, do you see the derivative now? Now you see the derivative. Okay. I think everybody sees the derivative now. Right? Good. I haven't forgotten your question, okay? All right, good. So that means that I can define this if it exists. And that would be the overnight lending rate, what used to be called Libor. I say used to be called because Libor has been phased out. There's some issues with Libor, okay? But we can still think of the overnight lending rate, and for sure we can think of this curve as, the derivative of that, right? Good. So that's my first definition. But now I have to address your question. Why does this derivative exist? And this, I don't know. I don't know that it exists because I don't know what properties my function R is going to have. In fact, let me argue. Actually, you know what?
You can take a weak derivative.
I know. But at some point, I'm going to, very soon, in about 15 minutes, I'm going to link this to your assignment number 1. Okay? Make sure I address your question before I finish explaining assignment number 1, because your question has a very important implication on assignment number 1. In assignment number 1, I'm going to ask you to calculate the yield curve and something that I'm about to define, which is the forward rate, for which you will also have to take a derivative. The thing is that you're going to calculate a discrete curve. You're not going to calculate your curve is going to be like that. And you're going to have to calculate the derivatives of this curve. In this curve, actually, it has no derivatives there, and there. It has no derivatives, right? You still have to calculate the derivative. So today we'll calculate derivatives like that. Yes, we could do it with a weak derivative. There's many ways to do that, but I'll talk about that when I talk about assignment number 1. I'll tell you how I want you to do it, okay? So let me ignore that for now, but that's a good question. So that's one thing. Now, to continue, I need to introduce now a new term, which is, I already mentioned this last week, but now it's going to become very important for us, which is forwards and futures. Forward and futures transactions. So a forward contract is a bilateral contract. We agree we're going to buy something from each other. We saw rice in Osaka, 17th century. We saw that last week, right? And now you can do that with oil, with gold, with many things. You can do that with stocks and bonds too, okay? Although the rationale as to why you would buy a bond and a stock in the future is, we'll see today, but it's less obvious than, say, rice, right? If you are a producer of rice, rice is still growing, it's still green, you can sell it now, but if you can lock in the price to sell it, say, 3 months from now, you would do it. That guarantees some income. You have a pretty good idea how much rice you're going to produce, right? Same for wheat, same for, how about oil? Oil, not cooking oil, oil, to make gasoline. Oil is only bought and sold in a futures market. Why? Because if you want oil, they're going to what? Bring a tanker to your house now? No. You say, well, I want oil. When? Well, in a month. In a month, that's nothing. How about 6 months, right? You have to be in the tanker over to your destination. So some things are always sold in the futures market. But there's a difference between forwards and futures. They work seemingly the same. You agree on a price. You agree now, you pay later when upon delivery. It's like when you buy something of Actually, what happens when you buy something on Amazon? Is that a forward, a future, or a spot? What is it?
When you buy something on Amazon?
Amazon, yeah. It's going to be delivered to you, say, let's say you don't have Prime. It's given to you in a week.
Forward?
Actually, they charge you now. So that's not exactly it, right? Yeah, Amazon charges you and then they ship. Imagine that they ship and then they charge, right? Most of the online retailers, sorry?
I think they charge you after they ship. I think that's what they're doing now.
Oh, then you're lucky. They charge me immediately. As soon as I say buy, I say, okay, then I see the charge on my credit card, like within a second, okay? You may have a special plan. I'll sign up for yours. Yeah, me too. That's where I see they charge me immediately. You know? Okay, let's not go there. But what's the difference between a forward and a future contract? The difference is that in a forward contract, if I say I'm going to pay and then I don't, what happens? Well, you can sue me, you can take me to court, but essentially you're screwed, right? In a futures contract, it's guaranteed. There's a futures exchange that guarantees that transaction to go through. The futures exchange may have some risk to the participants, but the futures exchange guarantees that. It's not a bilateral transaction, okay? I may be buying, you may be selling, but at the end of the day, we transact through the exchange. This will become important in about 2 months when we see credit risk. 1.5 months, when we see credit risk. The difference is default. One has default risk, one has no default risk. But since we're not talking about that today, we're going to somehow ignore that. So let me spend some time talking about forwards and futures. They are the same today. They are the same, okay? Not only everybody works for free in the financial sector, also everybody does what they're supposed to do. Wow, a wonderful world, right? No, it's not a wonderful world, because then who will pay your salary, right? Then no one will be looking for a job. This room will be empty. No one will be taking my course. I don't think people take my course because of the math. I think they take my course because they want a job. Most people do. All right. So let's keep things the way they are. But at least for 2 months, we're going to assume. For a month, we're going to assume that everybody works for free. And for about 2 months, month and a half, we're going to assume that there is no default. Everybody does what they're supposed to do. Okay? Otherwise, the math becomes all of a sudden too complicated, and we need to start developing math one step at a time. So let's say that I want to sell you Apple stock a year from now. Let's say Apple stock is at 135. It's pretty close today. Let's say it's 135, and I say I want to sell it to you a year from now. What price shall we agree? Now, this is interesting. It may look like I'm trying to guess what Apple stock will be a year from now. And that, that I cannot do. I wish I could. No, I cannot do that. But I don't need to guess what Apple stock will be a year from now to have a transaction with you, a futures transaction on Apple stock now. I don't need to know what Apple stock is going to be. How do I do it?
You include the accrued interest.
What I do is the answer is yes, but I want to do it in a more systematic way, which is what I will need to develop for the rest of the lecture, okay? So I will build a replicating portfolio. I'm going to create a portfolio that has exactly the same cash flows as a forward transaction on Apple stock. And it's this. This is my replicating portfolio. Anybody wants to transact with me? Does anybody want to? It makes it easier if we do role playing. I like to do role playing. It's very hard to do on Zoom, but it's very easy to do here. Anybody here wants to trade with me? Yeah, you trade with me? Great. Okay, so you're going to buy Apple stock from me a year from now, and we need to agree on the price, right? And again, no one is making money, so we're not making money, okay? So you say, okay, great, this is what I do. I want to borrow $135 from someone. Someone wants to lend me some money? $135? Oh, wow, lots of people want to lend me money. I'll take your money, that's great. So, oh, wow, no one wants to transact with me, but they want to lend me money. That's great, I must look wonderful. Okay, so I'll borrow $135 from her, right? Your name? Cheryl. Cheryl, that's right, I remember now. And yours? Yandi, okay. So I borrow $135 from Cheryl, and then what do I do with it? I buy Apple stock, right? And what do I do with the Apple stock? Nothing. I keep it. A year from now, Yandi, yeah, you called me. I said, hey, my Apple stock. So, oh yeah, I forgot. Yeah, okay. So, oh, here it is. And I give it to you, right? And then I charge you X, right? And then I give you X. Good, and we'll go home happy. No one makes any money, no one loses any money. What is X? It's exactly what you said, right? So how much would you charge me to lend me $135 now that I will pay you back in a year? The thing is that you dictate that price, right? You say, well, you want $135 now, in a year you pay me $200. That's where you want to lend me money, right? Yeah? And then I say, well, $200. She sets the price, right? See? So this is important for two reasons. First, it helps us price a forward transaction, but it tells us something more. It tells us that the yield curve is the foundation for everything, right? Time is money, in fact, is more than that. Time is everything, because that's how we price all the transactions that are coming up today. If you say, no, I'll lend you $135 now for $150, then you price $150. And you're looking at me, but you're actually her. Cheryl is the one that is actually setting the price for the transaction, you see? Okay, good. And it's there. And this, by the way, is called the replicating portfolio. So I have to deliver something to you, and what I do is I create something on the side that it exactly covers me. And in this case, it's a lending agreement with you. All right. All clear? So it's easy to do a futures or forwards transaction on a stock, right? How about a bond? How about a bond? Let's do a forward transaction on a bond. Well, by the way, this is the formula, right? This is the formula to read the forward transaction of a stock to the yield curve. And this is done for all possible times and tenors, lowercase t, uppercase t. The forward transaction, the forward price of a stock has now this is called a term structure. We're quickly getting to that. It's a surface. That's a function of when I enter into the forward transaction and when do I have to deliver. Yeah? This is notation. This is clear, right? Yeah, okay, great. So let's say that I want to do this with a bond now. All right, so who wants to transact a bond with me now? You want your name? Kevin. So Kevin is going to transact. So you're going to buy a bond from me a year from now. Say a year, right? And let's say it's a bond. So what kind of a bond is it? Let's say a 2-year bond, right? A bond is not like a stock. A stock is just one thing. A bond, a year from now, you can have a 1-year bond, a 3-year bond, a 6-month, say a 2-year bond, right? Oh my goodness. So this is a bit more difficult, right? Because I have to give you I have to give you the price for a 2-year bond that I'm going to sell you a year from now. Understand? Okay. Is it more complicated? I'll borrow money. Are you willing to still lend me money, Cheryl? Yes? Okay, so you still, so I have my bank. She's there. Okay? So I can borrow as much as I want from her, but what do? I need a replicating portfolio, right? Yeah, what's my replicating portfolio? It's a bit more complicated. But it's key that we start to think in terms of replicating portfolios, because then we can price anything. Not only we can price anything, that's what transactional institutions, that's what they do. They sell something to you and then they trade something so that they can deliver to you what you want. Of course, they charge you a fee. No fees today. It's free, okay? But that's how they, so it may look like they take risk, and no, they don't take any risk, they just charge you a fee. And the income is for sure, right? Okay, so to create a replicating portfolio, we need to first understand what the cash flows are going to be. And so this is the portfolio I have. It's an agreement that we do now. The agreement is now, and now is lowercase t, yeah? I'm going to deliver something to you at uppercase T1 a year. That's the next date. That's the delivery date. And then I have to charge you something, which I don't know yet, so I'll give it a name. That's what mathematicians do when we don't know something, we give it a name. Call it P, but this P has 3 variables in it. Time today, T1, and T2 was the maturity of the bond. I'll give you a T1, right? And then the payment date is T1, not now, later. This is what I'm trying to replicate. And I was trying to replicate this, by the way, with instruments, financial instruments that exist now. You can say, well, it's a bond I'll buy a year from now. Yeah, I don't know what that is. I cannot buy it, right? The advantage of my Apple transaction is I can buy Apple stock now. A replicating portfolio has to be a portfolio I can build now. Okay? So this is what we do. Let's analyze the cash flows of this portfolio. What's the cash flow now? Nothing. Nothing. Don't think of Cheryl. You're all going to give me money, yes, but I'm pricing this transaction, not the other one, right? So this transaction with Kevin, right? Kevin is, we're exchanging nothing. We just signed a piece of paper. No cash flows. A year from now, yes, you pay me something, right? That's why I have a negative there. And then at T2, what happens? I give you $1, the bond. The mythical, mathematical, zero coupon bond with notional 1. I give you $1. So that's the cash flow of that transaction. Now what I need to do is I need to create another transaction, right, that matches those cash flows. Okay, what that would I can tell you is very simple, but can you come up with it? What would you do? How would you come up with this replicating portfolio? Yes?
I got a question.
Yes.
For futures contract, the prices are settled like on a daily basis. How would that affect cash flow?
Say that again?
Like for futures contracts, the prices are settled on a daily basis.
Okay. I think you know too much. Okay. It is true when you're doing a futures transaction. I mentioned earlier that the exchange, as I make or lose money, I will have to give them money or not, or they give me money, all right? It's called a variation margin. They do that, that's how they protect their default risk, okay? So in this transaction, because no one is going to default and no one is making any money, I don't have to do that. But thank you for pointing that out, because what I'm telling you here is unreal in that sense. Okay, so let's say it's a forward transaction. Let's say everybody is not going to default, so I don't need to do that. Okay, but yeah, you're right. He's right. He's right. Okay, in a transaction like this, as you buy oil or gold in the futures market and the price goes in your favor or especially against you, you have to put up a little bit more money as it goes against you to the exchange. That's how the exchange covers their risk. But we're not doing that here today. Yes?
Just wondering why P is negative.
Actually, P is positive. That's why I have a negative sign there, because one is money I get, the other one is money I give. That's why. Okay? Otherwise, if I imagine that in my cash flows is 0, positive, that means I make money. For sure, it shall be an arbitrage opportunity, right? It's just to reflect the direction of the cash. Of course, for me and for Kevin, there will be different signs, right? So here is my outflows That would be my outflow. So that's good. I get money from Kevin, and then I give money to Kevin. All right. Okay. So let's think. The clue is in T2. In T2, I need to generate $1. That means that my replicating portfolio should include a bond, notional 1, that matures at T2. That's going to be the source of the $1 I'm going to use to give you, right? That's clear. I'm walking you through the thought process. I can just show you the replicating portfolio and say, well, see, it matches, see, it matches, yeah, it matches. And then, but no, I want you to see how you come up with a replicating portfolio. Because I have to raise $1 to pay you, right? For sure, my replicating portfolio will contain a bond that matures at T2. All right? Okay. After that, the next key is here. The cash flow is now. So I could buy now a bond that matures at T2, yes. Right? But that's going to cost me some money. And I know Cheryl will lend me money, but I can't because this is a 0. So what do I do? What I do is I short sell some bonds that exactly give me the money I need to buy the bond that matures at T2. See what I mean? Are you following me? So we start here. That's number 1. That is going to tell me I need to buy a bond that matures at T2. But I cannot spend any money, not even with Cheryl's help. I can't, because my cash flow is 0. That means I need to raise some money to pay for this bond. I need to raise some money. Whatever this is, I have to raise. How do I raise this? I have to sell something. What can I sell? There's only one thing I can sell. What is it? What? Whoa. Someone spoke around that area, I think. Oh, you did, yes. So I sell a 0 coupon bond that matures at T1, right? But do I sell one bond? I have no idea what the price of that bond is going to be, right? So I have to sell enough of these bonds to give me exactly the money I need to buy this one. Understand? Okay, so I think we have a clue. Let me now show you the portfolio, and you will see that's exactly what I did. That's the portfolio, okay? So I construct a portfolio that contains one bond unit of that bond, that's the price, and then it contains minus X bond units of this one, where X is exactly that. Why did I pick X equals that? Who can tell me? I'll give you 10 seconds.
That's the ratio to buy. That's the ratio to buy or sell the bond.
But why? Two more seconds? Now.
So then your cash flow is 0?
To make my cash flow 0 now, right? Or in other words, it's exactly what I said earlier. If I short sell exactly that many units of that bond now, that gives me exactly the money I need to buy my bond that gives me $1 at T2. You see? That price kills the denominator and gives me the numerator, which is exactly what I need to buy for that bond. So Cheryl, I don't need you for this transaction. I'll need you later, okay? Is that clear? You may think, oh, but this is a fractional number of bonds. Yes, exactly, we're mathematicians today. We'll buy fractional numbers of anything. You can buy 10% of a bond. You can buy 0.001% of anything. Okay, just like Bitcoin, right? So this is my replicating transaction to buy a bond future. Is that clear? Now, but this is interesting. You may think, where's this going? Well, it's going to a very interesting place because, let me walk you through this now. We just climbed the mountain, by the way. We just climbed the mountain. The first mountain we climbed is this. That's the price for my forward transaction. My forward bond trade gives me that price, right? And there's no math here. There's no math. This is all real transactions with bonds, right? And I can buy this and borrow that, or short sell this, and then I have the money I need for you. That's all real finance. But now that we see how that works, we think maybe we should mathematize this. Maybe we should create some mathematical constructs that explain this situation. Before we do that, let me justify you why this is important. Okay? Let me justify this to you, why this is important. And for that, I'm going to drop my iPad and I'm going to talk to you. Because I explained earlier doing a forward transaction on Apple. And I think that was a big deal, right? I don't know why anybody would do that. But how about a forward transaction on a bond? Why would anybody do that? I want you to understand why someone would do a forward transaction on a bond. Who are the main buyers of bonds? Say something. Could you think buys bonds all day long?
Pensions.
Pensions. Pensions, exactly. Why? Pensions. Remember we talked about pensions last week? What did I say about pensions? I said two things. The best pensions are in Canada, actually in Toronto. So look for jobs there. And you're not too young to think about retirement. No one is, all right? You're all paying pension contributions through your CPP something, right? What is the job of a pension? The job of a pension is you give them money, and the money you give them somehow is not going to just disappear through the rivers of inflation. It's going to grow through the rivers of inflation. So when you retire, that money is worth something, right? That's their specialty. They can put that money to work so that when you retire, you have something which was similar to what you contributed, but in dollars of 40 years from now for you, 5 years from now for me, right? That's what they do. How do they do that? By buying Apple? By buying Bitcoin? No. The main thing they do is they buy bonds in a very smart way, right? They can't just buy bonds making that value the share. So they have to be smart how they buy those bonds. And they have bond traders, and maybe one of you will be there and say, oh, you know what? We need to buy $100 million of this bond like now because it's good, right? What are interest rates now, high or low? You probably already started assignment number 1, so you may know. They're going up, right? This was the news. For how long have they been going up? For how long? For a year and a half, right? They've been going up like 50 beeps, 50 basis points, 0.5%, like every 3 months. Like that's a lot, right? By the way, they were very, very low 2-3 years ago. They were like 0. They were even negative at times, right? What happens when rates go up?
Money is more expensive.
Money is more expensive, but bonds are cheaper. Bonds are cheaper, right? So let's say that you think, wow, bond rates are going up, so bonds will be even cheaper, right? Yeah? And you're a pension. And what do pensions get? Monthly cash flows. You make monthly contributions to a pension, right? Yes? So every month they get $100 million, $1 billion. And they have to do something with that money. Let's say they buy bonds. Let's ignore everything else in the pension portfolio for now. They buy bonds, right? And guess what? They know exactly how much money they're going to get next month. Because those contributions are very, very regular, right? And imagine this, you're a trader, you have this job, I said, oh my God, look at these bonds, they're so cheap. And I think this is not gonna last. I wish I could buy those bonds next month, when I know my next $100 million are coming in. But if I wait, it may be too late, right? What do you do? What do you do? You know there's $100 million coming next month. What do you do? You think, you said, who can buy me a bond? I'll pay you next month, okay? But give me the bond now. That's a bond forward transaction. You see? Bond forwards are a big deal. Bigger deal than stock forwards. Stocks have a different, they don't have that kind of buyers. You understand what I'm saying? You see the urgency of some of these bond traders to buy the bond next month now. I cannot pay you now, I have to pay you next month when my next $100 million come. And who knows, maybe I buy forwards for next month and the month after that and for the foreseeable future, because I see those rates are very cheap right now and they're gonna get higher. You see? That's why these markets exist. And that's why you need math to help you understand what these curves are doing. Because now this is not the yield curve anymore. This is the forward yield, whatever that is. What is it? We need to define it, right? Let's define it. Okay. Now I can get my iPad again. Let's define it. The price is there. There's no question about that. We know that. But how do we put this into a context where we can make decisions? We need math for that. So this is the first definition. And it's a definition, right? I'm going to define my forward yield the same way we defined the regular yield, by taking the logarithm and dividing by that. It's a definition. It's the forward yield. Good. There's something very interesting here now, which is I'm going to take a different limit. Do you remember the instantaneous cost of borrowing earlier, the spot rate? The short rate, sorry, the short rate. Well, we're going to do the limit when T1 goes to T2 in this expression. Everybody sees a derivative there? You see a derivative? You see a derivative. Now that's very clear. I don't have to add 0. Right? If T2 goes to T1, that's a derivative. That's a partial derivative. That one. That partial derivative has a name. It's called the forward rate. And it's the one that's going to give me the clue as to the transactions I want to do for bonds in the future. And this is something very interesting happening now, because from the forward rate, because look at this, F is equal to that. This is a differential equation that you can invert, right? The bond price will be equal to the exponential of that. You see? You've all taken differential equations, even those who don't have the prerequisites, yeah? There is something very significant here, which is that if my bond price can be written as a function of the forward curve has the same information as the yield curve. In other words, in taking that limit, there's no loss of information. The forward curve is actually a surface, it's a function of two variables, just like the yield curve. They're different from each other, right? But there's no information loss. Why? Because I can recover all the bond prices from the forward curve through that expression that we have there. This is very important because this means that we just finished, we're done. We just finished creating what's called the term structure of interest rates. We have created the yield curve earlier, another forward curve, which is equivalent to it. And with this, we know the price of money. So I can do forward transactions on stocks, with Cheryl's help, okay? And as you will see, lots of other things. We understand the value of money now. in very real terms, and with all of the mathematical constructs, we will need to understand that. Okay? Yeah? All right. At this point, what I want to do is I want to explain to you why assignment number 1 is important. Very important. And I don't know if I should do it before or after a break. What do you prefer? Kind of a question. Before? Okay, so I'll talk about assignment number 1. Okay. Do I have to put it on the screen, or everybody knows assignment number 1 now? Screen or screen? Screen, okay, screen. So I'm gonna stop this share and open a new one. Oh, there's something in the chat. Oh, sorry. People in Zoom are writing things in the chat I cannot read. If someone wants to have a Zoom session open and tell me otherwise, I will read this all this when it's finished. Okay, so let me now go to the assignment. On Zoom, oh. Can you see that? Oh, okay. All right, so let me see if I can. So the rest, I think I'm going to go to just see. No. Go. I don't know what's going on. I don't know. It's okay. There we go. All right. So you have to do certain things. You have to get bond data, and then you have to do yields to maturity. You have to calculate yields. That stuff is all fine. But then you have to calculate the yield curve. How are you going to do that? To calculate the yield curve, you have to find that curve that prices all those bonds simultaneously, right? How can you do that? How can you find a curve that prices? Well, every price is an equation. So conceptually, you have to solve a system of equations. That's what you have to do. A system of non-linear equations. They're non-linear because your unknown variable is on the exponent of an exponential, right? But it's a system of non-linear equations. You have to solve that. How can you solve that? How can you solve that? This is the clue. This is the clue. Maybe I should actually, I don't know if I should. I don't know if I should do this on my presentation or here. I don't know. Maybe I'll do it here. Okay. Can you get the yield curve for all maturities less than 6 months? Yes. Very easily. How? Because the maturities less than 6 months lead to bonds which have no coupon payments left. So it's a logarithm and a division, right? You all with me on that? The yield curve up to 6 months is a joke. Actually, it's not even funny. It's easy. Logarithm and a division. You all with me? You all with me? Yeah? Shall I put it up, the equation? No? How about the bonds which are between 6 months and a year? They have a coupon payment. Therefore, they have two cash flows, not one, but two cash flows.
One of the cash flows is already determined.
One of the cash flows happens in less than 6 months. And the thing is, because the yield curve prices everything, that cash flow is already priced by the yield curve you calculated earlier, right? So that rate is not an unknown for that particular equation. So of the two terms that appear, one is not an unknown, is an actual number. Once you solve the first equation. So then you solve for the second rate, which comes from the second payment. That means that you can get all of the yield rates now between 6 months and a year. Again, each equation has two terms, one of which is now a number after you solve the first equation. This is similar to the way you do Gaussian elimination, the way you solve linear systems of equations. Remember, if I give you a triangular system of equations, which is the whole point of Gaussian elimination, then how do you solve that? You start with the equation that has only one term. That gives you an unknown. You plug it into the equation with two terms, so you solve for the one term. And then you take those two values, you go to the third equation, right? And then it's called bootstrapping. It's not a statistical bootstrapping, it's the way you tie your boots, right? So here we're doing the same thing. We solve the yield curve in chunks of 6 months. Recursively. And the key is that every time we solve for the yield curve in a chunk of 6 months, we can go 6 more months and get one equation with another coupon payment there, right? That's how you do it. So not only this yield curve exists, we now have an algorithm to compute it, which is to do this in an increasing manner, going from simple equations to more complicated equations. So that's how you solve the yield curve. Now, once you have the yield curve, of course, you're going to have to make some assumptions. Why? Because when I say that you calculate the curve for 6 months, it's actually not 6 months. It's a few points in 6 months, right? There's infinitely many time values between now and 6 months. You're only getting a few. So what do you do for the rest which are not in your curve? You interpolate, right? Sure, by interpolating, you are destroying the beautiful edifice we build with math. Sure, but you got to do something. What interpolation are you going to do? Linear. Some of you think, oh, I've taken this course, I'm the king or the queen of spline interpolation. Don't. Even if you're the king or the queen of spline, please don't. Spline interpolation creates very unneeded and very unpleasant oscillations in the yield curve. Not good. Don't do that. Do linear. Do linear. Okay? Yeah.
Why is it not exponential?
Okay. Do linear. Okay? Let me leave it like that. Let me do it like that. Yeah, do linear. This is a fantastic topic. I think there are still people doing research on this today. Okay, there's entropy, interpolation, it's fantastic. Do linear. All right? Now, when you do linear, what happens? And now it goes back to your question. What happens when you do linear interpolation? Linear interpolation creates kinks, right? Big deal. But at some point, I also ask you to calculate the forward curve. The forward curve is what? You don't have to do anything like create a replicating portfolio. No. We already have a formula. It's in the notes. It's an expression involving a partial derivative. You have to take the partial derivative of your yield curve to go to the forward curve. Just look at the notes and follow your notes, okay? But how do you take the derivative of something which is like this? You will have to take a derivative of this at that point for the forward curve. You will have to. How do you do it?
You just take the limit as your first thing.
What I would do is this has one value, this has another value, I take the average. Yeah? Do that. Do that. Do that. Okay? And that gives you the yield curve and the forward curve. Now, if you continue reading the assignment number 1, you're all with me here? Yes? Oh, it's all clear, right? By the way, guaranteed you will learn a lot doing this assignment. A lot. Even if you've been doing bond trading for 10 years, you will learn a lot. You will see. Because another thing I ask you to do here is I ask you to do, where is my next, sorry, I'm going to have to restart this. Here we go. All right, so it's, okay, so in point 5, yeah, there it is, you see? Can I move it? No. Oh. Okay, it's very difficult to do here. Okay, maybe I should. Okay, so I think I'm going to bring it down. Well, okay. Sorry, I'll go to my iPad. Point 5. This is the most important part of the assignment. It's here. Here I ask you to do this. You're seeing, say, 5 rates changing daily, okay? And then I ask you to consider these rates as a vector, as a random vector, and calculate the variance-covariance matrix of the logarithmic changes of these rates. What does that mean? It's very, very simple, very, very simple. Let's say that you look at one rate, it's 1%, and tomorrow is 1.1%. It increased by 10%, right? Okay, so that change is 10%. 0.1, 10%. The next day is 1.2. It changed by 0.09%, okay? Next day, it dropped back to 1. So it went down by 20%, so minus 0.2. You're gonna look at the daily changes in this fashion that it's here. I don't know if you can see that, right? And then you're going to treat that as a random vector and calculate the variance-covariance matrix of that. Yes? Yes? Variance-covariance matrices, you haven't heard that for the first time here, right? You know that. Everybody knows variance-covariance matrix, yes? Yeah? Everybody? If not, go to the Wikipedia immediately and see what it's all about, okay? And actually, if you don't know the variance, you've never seen it before, you may have lots of difficulties in this course, right? And that should be a real, prerequisite. All right. And then I ask you to do something weird. I ask you to calculate the eigenvalues and eigenvectors of that variance-covariance matrix. Why? Anybody knows? Okay. The reason is what I will tell you after the break. I need 1 hour to answer that question. And it's really, really important because we climbed a mountain today, which is we can define these mathematical constructs on fixed income markets. But the thing is, we've also created a framework to understand the dynamics of that. And as you will see, this opens the door to another mountain that maybe you've already climbed before, maybe. If not, we'll climb it together after the break, which is how we can use information that comes from the variance-covariance matrix to understand how markets behave and what they actually do. And that's key. If you're going to do any trading and you don't know those market risk factors, which is the next topic in my presentation, then you will. I know a lot of bond traders. Many of them don't know a lot of math. This is the part where they feel most pain. Not understanding these dynamics we're about to do. But for that, you need to know eigenvalues and eigenvectors very well. All right? So yeah, I'm assuming your linear algebra is perfect, right? Yeah? Should be. Okay, so we take a 15-minute break, and after that, I will tell you how linear algebra matters to understand these dynamics. The next thing that I want to do is I want to show you, we climbed a mountain, and I want to show you the landscape from this mountain we just climbed. And in doing that, I will have to make a reference to things that I hope you know. I'll try to be as all-inclusive as I can. By the way, I just realized someone pointed out to me that the link to the YouTube playlist is not working on the website, okay? So I'll fix it. By 3 p.m. it should be fixed today. Okay, so, well, I have some things written here. Let me just go into the crux of it. Here's an example. Let me walk you through this example. This is an example of something pretty interesting. This is, I think it's 10 stocks. 1, 2, 3, 4, 5, say about 10 stocks. This is interesting what you do, not with 10, but 250, 500, S&P 500, for example, okay? But with 10, I can show you the results of the calculations. So I take 10 stocks, I look at their daily changes. It's very important when you look at financial data, you look at the daily changes in percentage points, not the actual dollar value. Very important. For those of you who know statistics, dollar values, they are mean reverting. No, sorry, not they're mean reverting, no. They have mean, they're autoregressive, okay, and therefore statistical calculations will be misleading. So it's very important that you have to, you need to look at what's called the differentiated series, which is essentially their returns. So you have to look at the percentage return, okay, between one number and the next. So you do that with stocks. So you have, in other words, you have to look at the percentage change of each stock, and that now for 10 stocks becomes a random vector of dimension 10. In your assignment, you're doing something similar with a random vector of dimension 5, I think it is, right? It's 5 bonds, I think I asked you to do. But here's 10. Doesn't matter. So when you do that, if it's a random vector dimension 10, I have a variance-covariance matrix which is 10 by 10. The matrix is not here, okay? It's a matrix there somewhere. It's not an interesting matrix. What's interesting is what happens to it when you look at its eigenvalues and eigenvectors. And that's what I have here. Okay, so what we have here is the eigenvalues and eigenvectors of the variance-covariance matrix of 10 stocks. For your assignment, you obtain something similar, except 5 by 5, and it's for rates, not for stocks, but the conclusion is the same. What I have highlighted here is the following thing. First, the eigenvalues. The eigenvalues are here, 2, 0.3, 0.69, 0.21, okay? This is the actual eigenvalues. I'm not interested in the eigenvalues as much as I'm interested in the relative size of the eigenvalue to the trace of the matrix. The trace is the sum of all of the eigenvalues, okay? Or the sum of the diagonal elements, as you probably know, is the same thing. This is your linear algebra at work. So what I can see here is that the first eigenvalue is more than 50% of the sum of all of them. It's very, very big. The others are smaller. Much smaller, okay? They continue to decrease, but see, from 50% you go to 10. and then 7, then 6, then 5, then 4, then 3, then 3, then... Okay? Why is that? Who can tell me? There's a lot of financial significance in that eigenvector being so high.
The risk of uncertainty.
The risk of...
Uncertainty.
Volatility.
Good answer. Anybody else?
Volatility.
Volatility. What happens is this. Who invests in stocks here? Anybody? You invest in stocks? Okay. I don't know if it's true or not, but I'll pretend that you are a very experienced stock trader, and then I'll talk to you. And okay. So you have a stock portfolio. I assume you go long only stocks. Okay, good. So if I tell you that Canadian or U.S. Both. Okay. So let's say U.S. Okay. Let's pretend you're U.S. Let's say I tell you that the S&P 500 went up big time today. That's good. Okay. You see? Are you invested in the S&P 500?
I'm losing those now.
Okay, you see, but you still thought it was good for you that the S&P 500 was good. Why? Why is it good if you invest in stocks? I tell you that one particular asset went up and you say, that's good. Why? You understand? Okay. How do you know that the S&P 500 affects the price of your stock portfolio? It's because of that eigenvalue. You see that? Let me look at the actual eigenvector. Look at the eigenvector here. What can you see when you look at that eigenvector? By the way, if you do not know eigenvalues and eigenvectors, do me a favor. Get up, leave immediately, and spend the rest of this week learning about eigenvalues and eigenvectors, and then come back to class next Monday. It's good for you. Okay, get up and leave. You can do it. No? You all know eigenvalues and eigenvectors? Yes? Good. All right, good. Okay, so what's remarkable about that?
It's all negative values.
No, eigenvalues are, the sign matters, but eigenvectors, I can multiply everything by 1,000,000 or by minus 1,000,000 and it still is an eigenvector, so no. What is relevant is that they're all more or less the same number, right? How do you calculate the S&P 500, more or less? You take 500 stocks and then you weight them more or less with the same number, right? That eigenvector is like the S&P 500. That's what's relevant about it. But you see, I didn't need an S&P committee to form that. That's formed by math, by looking at the daily changes of the stocks. There's no committee. That's the significance of eigenvalues and eigenvectors. They tell me what's going on. They tell me that the main direction of movement for this market is in that direction. That's why you're happy when I tell you that the first eigenvector is going up, because your portfolio is going to go up too. More than 50% significance. You see? You see this? Okay. In your assignment number 1, when you calculate your eigenvalues and eigenvectors, what do you think the first eigenvector is going to be? Have you ever been able to predict eigenvectors of matrices which are 5 by 5? Maybe not before, but now you can. Why? Because you have some sense of financial meaning. What do you think that eigenvector is going to be? You haven't done the assignment yet, I guess not. What do you think is going to be? Who wants to volunteer a crazy answer? Eigenvector. So you have 5 elements there. Who can volunteer an answer? Thank you for that. You.
All ones.
All ones, exactly. Why? Why? What is that eigenvector telling you? It's the same thing as with stocks, right? Except here we don't have stocks, we have rates. When rates go up, they typically all go up. And when they go down, they typically all go down. When the government of Canada, they tighten and they say it goes up by 50 bips, they all go up a little bit, or a lot. They move together. When they move together, that means that the eigenvector, they're all the same.
So can you explain again why they correlate? So you're basically saying
That's what the eigenvector is.
Yeah, but
Okay, so let me see. Let me do this very quick. What are you studying at this university? You're in this university,
Yes.
right? What are you studying?
deep learning.
No. What program?
I'm actually not a math, so math.
Math specialist?
I'm actually a PhD student.
You're a PhD student, so you may have heard about the variational inequality or the variational definition of eigenvalues and eigenvectors, yes?
Right.
Okay. So what eigenvalues, the largest eigenvector describes the main direction of movement, right? Who's any physicists here?
The Rayleigh quotient, is that what you're...
What?
The Rayleigh quotient? Is that
Yes. You know the Rayleigh quotient? Yes, exactly. That's what this is. That's what this is. Okay. If there is a physicist here, that's the ground state energy of a Hamiltonian system, for example. Okay. Quantum mechanics, right? Except that's the lowest. Here's the highest. Same thing, right? This is describing energy levels. That's what quantum mechanics is. Energy levels, right? Why is it called spectral theory? Spectral. The word spectral, where does it come from?
eigenvalue decomposition?
No. Spectral. The word specter comes from what? From Greek. It means what? Specter. Any Greek here? Specter. You don't know why it's called a spectral theory? Specter in Greek means picture. And when you are taking pictures of faraway galaxies, you only saw certain frequencies, not others. That was before Planck's constant and Schrödinger's equation. So how weird. Look at this picture and then only get certain frequencies. Now we know that these are the only frequencies that exist. There's nothing in between. Those are eigenvalues and eigenvectors. That's what's called spectral theory, right? Eigenvalues and eigenvectors were very old. Lewis Carroll, who wrote Alice in Wonderland, he knew about this. He wrote papers actually books on that stuff, right? And suddenly they came together in the 20th century. That's what we still call it spectral theory. But it's eigenvalues and eigenvectors, same as 300 years ago. So Alice in Wonderland, there you go. Okay? That's what they describe. So the Rayleigh principle or the quantum mechanics, Schrödinger's, it's all the same thing. It's all eigenvalues and eigenvectors. In our case, this tells us the direction in which markets move. Rates move together also, like stocks. And that's why your first eigenvector in your assignment, the eigenvector with the largest eigenvalue will be like 1, 1, 1, 1, 1. Or minus 0.3, minus 0.3, depends on how you scale it, because eigenvalues can be scaled by any arbitrary number, positive or negative. Right? Stocks move together, so do rates, yes?
Yeah, but why is this only the case for the first eigenvector and not for the rest?
Okay,
as well?
this is the difference between stocks and the fixed income market, because what is the second eigenvector you're going to get in your assignment? You cannot see it here, but in your assignment, you can predict what the second eigenvector is going to be. You need to know a little bit of economics and a little bit of math to answer that. But I can predict what that I can do magic. I can predict what the second eigenvector is going to be. You want to bet? I predict it's going to be something like this. Let's say you take 5. No, sorry, let me say you take 6. It's going to be 1, 1, 1, minus 1, minus 1, minus 1. Why? Because I know, and you know too, that the yield curve moves up and down, parallel shifts. When the Government eases rates, they go up and then they go down, right? But then the one that comes after that is when it tilts, which is, by the way, an inverted yield curve. It's well known to be a prediction of a recession and inflation, and we have that. So very likely, I'm curious, I don't know how big that second eigenvalue is going to be, but I know it's going to be the second eigenvalue, I know that. And every economist knows that, except they can't express it like this. And I know the third one too. The third one is something like +1, +1, -1, -1, +1, +1. Because we know that the third thing that is the change of convexity. Okay? You like that?
Can you explain how your prediction squares with that?
No, stocks are different. Because in stocks, what happens is the factors are different. And this is what Fama French discovered. You have large stocks, small stocks, you have technology stocks, and then it becomes murky. It's more difficult to do what's called factor analysis for stocks than it is to do it for bonds. By the way, if I did this for hedge funds, it's all noise. You know the difference between noise and eigenvalues describe music when they're high. When they're low, it's noise. Okay, maybe you know this. I don't know. Sorry, I'm coming to this, okay? Yeah. Maybe you know this. You know this? What is this? That's the wave operator, right? This is what describes vibrations. Anybody plays the guitar here? You play the guitar? Yeah? Anybody plays the piano? No? You play the piano? Piano? Yeah? Anybody plays the violin? Play the violin? Yeah, me too, by the way. Okay. What happens when you play the guitar?
You're just changing the frequency to change the frequency.
You're doing this, right? So what you have here is that you have a string that's vibrating, and what you have here is the eigenvalues and eigenvectors of the wave operator. This is what makes the string produce a sound. So the eigenvalues and eigenvectors are here. These are called the fundamental frequencies. When you play an E note on your string, what do you have? You have the E, but then if you look at this, you can see these videos on YouTube. People do that, are fantastic. You can see the strings vibrate, and you see exactly the notes of vibration. And we know this now. We discovered this in 1850. Joseph Fourier, he told us this, right? We know that any sound can be decomposed into the fundamental frequencies, which are the eigenvectors of that operator. And that's where you have, say you play the E string. Let's say that's the E string. That one there, the one that has the biggest vibration. And then you have this one here also playing, the one that goes through that note, which is an E an octave higher. It sounds an octave higher. And then this one in red is which one? Who can tell me? This is music theory. Who can tell me what that is? A B, the dominant. Anybody knows music here? Music theory? That's a B, that's a dominant. The B sounds when you play the E string. Okay? The dominant. When you go to that one, that's the E again. Right? And then you have a new one, the one in blue. Which one is that? That's the A. The A sound, the subdominant. And that's how you construct all of the sounds. When you play right? You also have somewhere down into the frequency range, when you play the E, you also have the G sharp, which sounds terrible. No, you have the D sharp, which sounds terrible with an E, right? It's like the horn in a truck when you play them together, right? It's still there, but with a very, very small frequency. That's why your it's just noise. Your ears cannot hear it. It's too soft. And that's why the guitar sounds very nice. Right? Anybody plays the trumpet here? No one plays trumpet. Drums? You play drums too? Oh my God. What happens when you play a drum? When you tune your drums? Timpani, yeah? Okay. See, for the drum, it's the same operator, except it's not the Laplacian. And it's in 2 dimensions, and it's on the circle, because your drum has this thing probably attached, right? So you know what the eigenfunctions are for this? They are Bessel functions. They're not as nice as the sine and the cosine. That's why it's so hard to tune your drum. The guitar is easy to tune, because the frequencies, they die, and they all sound so great together. The sine function is wonderful. The Bessel functions are terrible, right? Much more difficult to tune. But it's the same theory and the same eigenvalues and eigenvectors. That's why I say when you look at something like this, you have music and noise. Music is what you can hear, the things with a very high frequency. In the case of fixed income markets, is the parallel shifts, the tilting, which gives you inflation and recession, and then the convexity. And then the rest is noise. Bond traders cannot go beyond 3. Bit rate, that would be what you use in music, right? The bit rate. By the way, this is how MP3 technology works. So the MP3 technology applied to financial markets, in the case of fixed income, is very simple. 3 bit rate, that's all you need. If you can control these 3 risk factors, you're in shape, good shape. Stocks are more complicated. Technology stocks, large cap, small cap, more complicated, right? You will see that in your assignment number 1. So watch at those 3 eigenvalues. That's your MP3. The rest is noise. You can throw away. And you tell me if it sounds like that. You understand what I'm saying? Now, this is a big deal. This is a very big deal. In this course, I only can scratch the surface. Here's, for example, the comparison of 2 markets. This is the stock market and the hedge fund market. The stock market has this very high dominant sound, and the rest is noise. Very hard to trade there. By the way, that's where you make your money, okay? Trading the S&P 500, so you're trading with millions of people, is very hard to differentiate. You just hope to get lucky. And you know that over time you get lucky. Why? Because there's millions of CEOs working for you to make their shareholder value higher, right? Okay? But if you want to trade, it's very hard. What hedge funds do is, as we will see at one of the last lectures of this course, is buy and sell. By buying and selling, they start taking differences between eigenvalues, right? And most of what they do is noise. It's very hard to detect any fundamental frequency, like in a guitar. That's why they are like that. There still is some market direction, because at the end of the day, they all have the same dependence on volatility and other things, right? But you can see that very marked difference from the spectral explanation of these 2 markets, stocks and hedge funds. But fixed income is the easiest, and you will see that in your assignment. All right? Okay, now, see this, by the way, this is some interesting, I'm not sure if you know this, but basically every time you look at your frequency, every time that n is a prime number, you have a new note, right? Every time n is a composite number is the same note, but octaves higher. So there's as many notes as prime numbers, and we know there's infinitely many prime numbers. Oh, Pythagoras knew this, by the way, right? So how many notes in music notation do we have? 12. Why? Why do we have 12? You know why? It's fantastic. Because 3 to the power 12. 3 is, you probably know the circle of fifths, right? A fifth, you multiply the frequency by the length by 3. The thing is that 3 to the power 12 is very close to 2 to the power 19. That means that if you follow the circle of fifths 12 times, you end up at the same note. That's what they say. It's not exactly the same. It's 19 octaves higher than the original one. Not exactly, cannot be exact, because a power of 3 cannot be a power of 2. But very, very close. You cannot hear the difference. And that's why Bach wrote the Well-Tempered Clavier, his very famous work with 12 tonalities. Okay? All of this is there. We need 12 notes. In the fixed income market, we need 3. Okay? Now, I want to say something here, and actually Leslie Lampert will say it better than me. I have a very short video, Leslie Lampert, and I want you to hear it, because what I'm telling you here, he will do it better than me. For that, I need to do, as usual, pass my mic to, the people on Zoom. I'm not sure if you can hear it. I'm going to have to reshare. Hold on. Okay. Now we watch this and listen carefully. This explains the difference between programming and coding that I mentioned last week. All right? It's very relevant for what we're talking here. Sorry, something's wrong with my sound. Sorry.
My name is Leslie Lamport, and I am a computer scientist, which is something that didn't really exist when I started being a computer scientist, and it took me a while to figure out that I was one. My relationship with computers began as a programmer. It never quite occurred to me that I was doing anything scientific until after I had published enough papers that it finally occurred to me. My education was as a mathematician. It was just natural for me to think about computers as a mathematician. When you write an algorithm, you need to have a proof that it's correct. An algorithm without a proof is a conjecture. It's not a theorem. And if you're proving things, well, that means mathematics. Computer scientists tend to think in terms of programming languages. One of the epiphanies in my career was the realization that I was not writing programs as a computer scientist, I was designing algorithms. I came to realize that if I'm not writing a program, I shouldn't use a programming language. People confuse programming with coding. Coding is to programming what typing is to writing. Writing is something that involves mental effort. You're thinking about what you're going to say. The words have some importance, but in some sense, even they are secondary to the ideas. In the same way, programs are built on ideas. They have to do something. And what they're supposed to do, is like what writing is supposed to convey. If people are trying to learn programming by being taught to code, well, they're being taught writing by being taught how to type. And that doesn't make much sense. The best way I have for teaching about programming, as distinct from coding, is to think about what the program is supposed to do mathematically. There's a very big practical problem with this. The mathematical education in this country is pretty terrible. Most people wind up being afraid of mathematics. This is even senior programmers. I've developed a language called TLA+ for writing down the ideas that go into the program before you do any coding. It's a pretty hard thing for engineers to get into, but when they do, it develops their ability to think mathematically.
I think I'm going to stop
distributed
it.
system is one in which
your computer
I'm going to stop it here. It
can be rendered
continues,
useless
but I think you got the
by
gist
the
of it,
failure
right?
of a computer that you didn't even know existed. Non-distributed.
Because now it talks about distributed systems. It's all very interesting. You can watch the video on your own. I think it's on my website. I'm not sure. Did you get it? And you understand? And this is very relevant because
Computing.
this is very relevant because it describes in a completely different context very well the relationship that I recommend you have with finance when it comes to the use of mathematics. And I think I just give you an example, right? You look at covariance metrics, you look at eigenvalues, and they have to have meaning to you. Maybe there's no need to prove a theorem. The theorem has already been proved, hundreds of years ago. The spectral interpretation of eigenvalues is very well known. I don't know if they taught you that when you did linear algebra. When I teach linear algebra, I do that. I cannot explain linear algebra without explaining music. It doesn't make sense to me, right? Because we all hear linear algebra every day. And the same thing when you go to markets. Now, I should tell you that today, I wanted to add an addendum to what this is something that I like to do this very much, but this time I'm going to do something that I've never done before, which is to explain a more modern way of doing this, so you know, because a lot of you are experts on machine learning, artificial intelligence, all of that, and there is a way that you can build on this with a lot of that. And let me just spend a little bit of time explaining to you what, using the example of a regression tree, how you can take these ideas and go even further. So let's say that, for example, I want to understand the relationship between the company size and volatility, right? And everything that I did today here has been from the ground up, the way we do traditional math. But artificial intelligence changes things. You look at the data and then you derive the rules from the data, not by thinking, right? It's different from but you can do this too. And in a certain sense, I give you a way of thinking about relationships today through eigenvalues and eigenvectors. And that's what we defined all of these yield curves and forward curves and all of that, because they have meaning. Today, when you go and work in the financial sector, you will probably be encountering the same or similar situations, but you will see that you're not going to be building them from the ground up like we have today. There's an alternative way, and that's what artificial intelligence, data science, and machine learning does. And but at the end, you're looking for the same expression. You want to understand relationships. And so one way of doing that, I hope you already know that. If you don't know regression trees, then maybe it's as if you don't know eigenvalues, and then you didn't understand what I said. But I know that everybody knows eigenvalues and eigenvectors. Regression trees, I'm not so sure. But let me just tell you that there is a way of doing something similar to understand relationships. And I use this example of companies, say some volatility. Let's say that I have this data given to me. And as you know, in artificial intelligence, it's all in the data. Then there is a way to find a partition that makes what's called the residual sum of squares, RSS, minimized. Okay, and this is the way you can start doing clustering, which is, again, grouping things, making relationships matter. And there's an algorithm for that. And an algorithm, as Leslie Lampert said, is really the proof that you converge somewhere. So this is like eigenvalues and eigenvectors, but at a different dimension. And you start by figuring out all the possible hyperplanes that could derive your data to minimize that residual sum of squares. It's an exercise in optimization, both combinatorial as well as integer optimization, right? And that is how you start deciding how you're going to slice. So in this particular case, you realize that the best hyperplane that will divide your data is the one that gives you the the division on the green and the rest of your data, and then you can continue with the rest of the data and then have the red and the rest of the data, and that's how you do clustering. This is essentially what a regression tree does for you. This is especially useful for stocks. As I mentioned to you, fixed income is easier. MP3 technology works very well on 3 factors, that's all you need. But for stocks or other things, you need better. And this is why some of these techniques are, you will see a lot more artificial intelligence used in stocks than on bonds. Fixed income markets are fairly simple. Your assignment number 1 is going to be, I think, good enough. Okay? And, well, I have some, you probably know this, I don't want to spend too much time on this. But when, I will end today's class with this. I have a meeting at 2, I have to go somewhere, so I want to finish, I want to end before 2. You probably know that when you're creating an artificial intelligence model, there is, it's only the data, the information is in that you have to extract it, and there's 2 very relevant sets of data. One is the training data on which you basically learn your algorithm, and then is the testing data set where you test that your algorithm is any good. This is different from what Leslie Lambert was saying in his video. He was a programmer where he needs things to have proofs. A lot of the artificial intelligence that we have now doesn't have a proof. Google Translate works very, very well, and no one can prove why. Well, some people have proved things on which it's built, so we're not entirely surprised that it performs very well. But this is how you run validation systems on the data that is that's given to you. So I think I'm just going to leave it here. No, I'm going to leave it here. I'm not going to. I just want to mention this as a way to tell you that in your assignment number 1, you're going to be able to mathematically build a very nice internal order into your system of yield rates. And that works very well, you will see. It's remarkable. When you're taking that away from those very well-ordered systems like rates, you will see that there is a need for sometimes more eigenvalues, more eigenvectors, but oftentimes it's a different type of math. Like in this case, regression trees are now used ubiquitously. They are very ubiquitous in the analysis of financial objects. Okay. So I think that's all I wanted to say today. Any questions? All right. So in your assignment number 1, I made a mistake with the dates when I posted it, so that's why I think I sent an announcement. Not everybody got it, it seems, on Quercus, where initially I asked you to start collecting bond data last Monday, and now I allow you to start collecting bond data today. It's easier if you collect the data on a daily basis. There is a way to go back and get the data, and she knows how to do that, but it's a bit more complicated. It's better if you develop the discipline of getting the data every day, and which is what I encourage you to do, okay? And you don't have to take the data for every single bond. You just, you can do that in a fairly rapid way every day. Yes?
Yeah, I have a question, like, because we need to collect the closed price.
Yeah.
And when this closed
No, take a price. Take a price. I mean, the prices do not fluctuate that much. Okay, we are assuming you will look at the data towards the end of the day, but if you do it in the morning, then you will pick some other price. Yeah.
Or so actually, everyone maybe have a different data.
That's okay. Yeah. I mean, we're not gonna check that you all got the same answer.